Hey, I'm Dr. T, and welcome to my whiteboard. So today I'd like to talk a bit about solutions, and over here I have a model solution. So in this case, I've got two chemicals, the blue dots and the orange dots. Exciting. Okay, so a solution is going to be a homogeneous mixture. It's going to look like one substance even though it's really a mixture of multiple. There's at least two players in a solution. There can be quite a few more. Solutions can be incredibly complicated. In all cases, there's going to be one solvent. Now, once again, English is English. It can be a little kooky, so sometimes we talk about solvents as being mixtures themselves. But when we're focusing on the solvent, we're talking about one particular chemical. And this is going to be the chemical that's dominant. Now, quite often we think of this as water, because water is very common. It's a very useful chemical for making solutions with, but it does not have to be water. And there are many solutions that have absolutely no water with them at all. Or in some cases, the solvent, even though the solution contains water, is not the water. Because, once again, with the solvent, it has to be the one that's in the majority. There has to be the dominant chemical in your solution. And, hey, if you've got honey, it's actually the sugar, not the water. Okay, so I've got this one. My blue dots, as you notice, they're in the dominant position. There's the most of them. All other chemicals in your solution are what's known as solutes. These are the things that are dissolved in your solution. Now, I only have one solute, the orange dots, but I can have hundreds, thousands of them. Obviously, things like, seawater, blood, etc. are complicated mixtures worth of stuff. Now, when it comes to solutions, I do want to briefly mention that there's a couple other players. So I can have solutions. These are the homogeneous ones. However, depending on the size of my particles, things can get a little bit more interesting. Solutions are typically going to be things like atoms, ions, small molecules, nothing too big and fancy. However, if I start increasing the size of my particle, then things get a little bit more interesting. So I can go up to a medium-sized particle, a particle between about 1 and 1,000 nanometers, and this is what we call a colloid. Now, solutions are clear. You can see through them. They may be colored, so it doesn't mean they don't absorb light. It means that they don't scatter or disturb the light. You'll be able to see through it, although maybe darkly. That said, colloids, think something like milk is going to scatter the light, depending on how intense the colloid is. It may depend on how much the light gets scattered. Of course, you can see that with smoke, etc. Other classic cases of colloids. Now, if I go a little bit larger, I can get a suspension. These, of course, have a larger particle. These are going to be over about 1,000 nanometers. And in this case, not only will it scatter light, it definitely can be completely opaque. In both cases, you can get pretty opaque, but the suspensions are notorious for doing this. Think silty water in this case. These will also settle out. So a suspension, the particles are large enough that gravity is going to have a meaningful effect on them, and they will sink over time. So a suspension can be separated simply by letting it sit. That's actually how deltas are formed at the end of rivers. The river slows down, the particles fall, and you get yourself a nice delta. Now, you've got a couple other options for separating out these guys. Solutions are actually tremendously difficult to separate out. There are ways of doing it, of course. Typically by trying to remove the solvent, boiling off whatever particular solvent happens to be. And there are, of course, other approaches that we will talk about. Colloids, you get another interesting approach, and that's known as dialysis. In this case, you take a semi-permeable membrane, and you can get it so it's down tight enough that it can even start separating out some of your solutions. But that is definitely more difficult. The idea here is that you've got a membrane, a thin either plastic or alternative source material, that allows tiny particles through, but the larger particles of the colloid or of suspensions get blocked. Yay, we have dialysis. Now, with suspensions, the particles are actually large enough we can do a technique known as filtration. And, of course, if you've ever made coffee, you know exactly what filtration is. You take, once again, not really a membrane, we call it a filter because it's much heavier. The holes are much larger, and, well, the holes are still too small for the suspension to go through, but the colloids and solutions typically can get through those holes. So, yay, we have ourselves some filtration. Let's talk a little bit about what happens when a substance actually dissolves. Of course, this is going to depend on what the substance and your solvent are. Since water is such an important solvent, we'll be focusing a bit more on aqueous systems or water-based systems than we will other solvent systems. Either similar stories will happen or a more simplified story is usually the case with other solvents, although once again, it depends entirely on what solvents we're dealing with. So let's take a look at some water or an aqueous system. And in this case, I've got a lattice. Presumably, this is some kind of salt crystal, with the reds being cations and the greens being anions. Obviously, there's a bit more to this story depending on what you go with. But you're going to have your lattice. And if this is going to be soluble, something that's going to be able to break apart and go into solution, then you're going to start splitting apart your lattice. Now, if these are cations and anions, that's a fairly straightforward process. The somewhat negative charge on the oxygen will be attracted to the cations. The somewhat positive charge on the hydrogen will be attracted to the anions. And they're going to be able to surround those and pull them apart from the lattice. Now, some lattices are more stable than others. So you'll find that some ionic compounds, water is very easily able to pull apart the lattice and dissolve. Others, it basically can't. That lattice is way too strong, and thus the water will simply sit around here and nothing will happen, what we call insoluble substances. For the most part, there's, of course, an intermediate. There's a continuum between completely insoluble and completely soluble. If this is not an ionic compound, then water's going to do very much the same approach, except for the fact that there's no particular cations or anions involved. Because it's not an ionic compound, there are no cations or anions to begin with. Now, I would like to point out a couple of different scenarios. Now, what I've described involves an ionic compound completely disassociating into constituent ions. That's what we call a strong electrolyte. You're going to go from your presumably solid ionic compound, although, once again, it doesn't have to be ionic. There are molecular compounds where things like hydrochloric acid, you'll have a covalent bond between the chlorine and the hydrogen, but that bond is so polar that it can break apart and form H plus and Cl minus. The H plus actually piggybacks on a water molecule, but that's kind of another story. These are what we call strong electrolytes. When they dissolve in an aqueous system, so dissolve in water, the water surrounds them, they completely disassociate, at least under reasonable concentrations. Obviously, if you cram enough junk in it, it's going to sit there. You can overload, you can saturate your solvent very easily in many cases. But assuming you haven't done that, a strong electrolyte is going to completely disassociate, you're going to get all of these ions as free-floating ions. And that's actually going to be quite important for us. The reason we call these electrolytes is because water itself does not conduct electricity. You're thinking, yes it does. No, it doesn't. What's in it can. And strong electrolytes are going to impart the ability of water to conduct electricity. Electricity is the conduction of charge. Water molecules don't have a charge. Ions, on the other hand, do. So if I want to conduct an electric current through it, all the anions go one way, all the cations go the other way. Maybe not all of them, but a good clump of them. And a strong electrolyte, you get the full bang for your buck. Now, opposed to a strong electrolyte is what we call a weak electrolyte. In this case, you will still dissolve, but you will have some that are ions and some that are free-floating, potentially molecules or clumps of atoms. So you can have ionic compounds that will do this too, but normally we think of molecular compounds. Most of your organic acids are going to be in this category, where they will sometimes break up, sometimes not, and they will interchange back and forth. We will have an equilibrium between both the uncharged together form and the disassociated form. Now, there are other compounds, particularly molecules, that will dissolve in aqueous solutions, but they don't break apart. If you think of the classic sugar or sucrose, you put that in water, you have a sugar crystal, and each sugar molecule will disattach from the sugar crystal, very much like I have over here, same basic story, except for the fact that the sugar molecules aren't ions. These wouldn't be positively or negatively charged over here, they're simply sugar molecules. They're polar, but they're not ions. For these, we call them non-electrolytes, because they're not an electrolyte. They don't have charge, they don't conduct electricity. So weak electrolytes, they conduct electricity, but for the same concentration, not as well as the strong. Now, that is a point. The amount you have doesn't actually relate to whether it's strong or weak. This is how readily it's going to disassociate. Of course, there is another choice that has been alluded to beforehand. It could just sit there. Not everything dissolves. Not everything is going to be compatible with every solvent. Polar solvents, such as water, tend to prefer compounds that are either ionic in nature or that are polar themselves. A metaphor we like to call like dissolves like. Non-polar solvents, things like hexane, tend to prefer non-polar solutes. They're able to interact and they get along quite well. But not everything. Not all ionic compounds will dissociate in water. And, of course, not all molecular compounds will associate with water either. Now, the fact that ionic compounds disassociate into their constituent ions when dissolved in water, assuming they are able to dissolve in water, this does start affecting the way we think about double displacement reactions, especially those that are precipitation reactions. So above me I have a classic precipitation reaction. In this case I have lead nitrate reacting with potassium iodide and forming lead iodide and potassium nitrate. This is what I call the molecular equation. Molecular equations are written the way you would write it in the old equation, just showing the formula units as formula units, not as ions in particular. These could be molecules. These are not molecules, but they could be. I'm not highlighting the ionic nature of this. Now, I can break these apart into their constituent ions, the way you would start to actually see them in solution. So I would have my lead 2+, my nitrate, and you notice how lead has 2 nitrates with it. It's going to give me 2 nitrates. Yeah, that 2 now becomes that 2. Potassium iodide is going to become 2 potassiums and 2 iodides. I'm basically distributing my coefficients through, and when the subscripts are kicking up and representing multiple of a particular ion that's going to dissociate separately, then those are going to be affiliated as a coefficient as well. Now you'll notice the O3, that still stays there. This is not 6O. That's because this guy doesn't disassociate. He's a polyatomic ion. Now, lead 2 iodide is still listed as PbI2. This is now a solid. This is a lattice structure that is too strong for the water to break apart. So this will become a solid. It's insoluble. Once again, not all ionic compounds are soluble. Good deal of them are insoluble, or at least only partially soluble. And then we still have the potassium and the nitrate left over, just kind of sitting around watching. In fact, the fact that they're just sitting around effectively watching is why we call them spectator ions. Spectator ions are just there. They don't particularly do anything of interest. So we can actually take what we call our ionic equation, an equation that highlights all of the ions involved, disassociated as they would actually be in your solution that is reacting. And we can remove all of the spectator ions. We just simply omit them because, once again, they're just watching. They're not doing anything. What we get is the net ionic equation, and the net ionic equation is showing parts that change. In this case, I have lead 2 ion, I have a pair of iodide anions, and then these form a lattice structure that is insoluble. So it's no longer ionic. It has now changed. With that said, have a wonderful day.